Look closely at these 18 glowing dots. They're microscopic specks of plastic darting around in a pitch-black vacuum chamber. To a human observer, their movement looks completely random, but the chaotic dance of these specific specks reveals the same mechanical laws that drive cancer metastasis through the human body. This experiment takes place inside a specialized environment filled with something called dusty plasma. We are used to interacting with solids, liquids, and gases, but on a cosmic scale, those are the exceptions. Plasma is the default state of existence, making up 99.9% of the observable universe. When you look up at the sky, almost everything you see is plasma. Our sun is a massive, boiling ball of the stuff. The only real exception in the night sky is the tiny bit of light reflecting off the hard, solid rock of our moon. But you don't have to leave Earth to find it. Auroras are plasma. And every lightning strike that connects with a building is a temporary channel of plasma right here in our atmosphere. Understanding the mechanics of plasma is not about studying an obscure scientific anomaly. It is about decoding the operating system running nearly the entire universe. Dusty plasma is exactly what it sounds like. It is a standard plasma environment, but with tiny, electrically charged dust particles scattered into the mix. If you have just 2 of those charged particles, figuring out how they interact is straightforward. Opposites attract, likes repel. That is middle school physics. But throw dozens of charged particles into the mix and you trigger the many-body problem. Suddenly, every single speck is simultaneously pushing, pulling, and reacting to every other speck in the room. It functions like a chaotic mosh pit where everyone is shoving each other at the exact same time with varying degrees of strength. Physicists successfully recorded the 3-dimensional movements of these particles down to the millisecond. They had all the data. But when human researchers stared at the footage, trying to map the interacting forces, the math became overwhelming. They could only see random noise. The rules of physics were absolutely still operating inside that chamber, but human cognition and the traditional mathematical equations we rely on hit a hard ceiling when trying to extract order from that dense web of chaos. A team of physicists at Emory University realized that human math wasn't going to crack this. Instead, they built a custom AI and fed it the raw video footage. This was not a large language model like ChatGPT. Those require billions of text documents. This new system was engineered specifically to look at a tiny dataset, just a few minutes of bouncing plastic dust. They built what is called a graph neural network. This specific diagram shows exactly how the AI perceives the physics problem. It treats every single particle as a distinct node and connects them with invisible threads, representing the potential forces between them. The AI's job is to rapidly test different mathematical values across those connecting threads. It guesses how strong a force might be or what direction it flows, to see which combination actually matches the real-world footage. It guesses, runs a simulation, compares the result to the recorded video, finds the errors, and corrects its own math millions of times within a single second. Because this network was built to be transparent, the physicists could look inside and extract the exact formula it generated. The AI transitioned from a data processing assistant to a primary scientific discoverer. What that AI discovered was a non-reciprocal force. It is a dynamic that contradicts our everyday experience of physical laws. According to Newton's third law, every action has an equal and opposite reaction. When you push a heavy wall, the wall pushes back against your hands with the exact same amount of force. But inside the dusty plasma, the AI found something else. Particle A exerts a pulling force, dragging particle B toward it. But particle B is simultaneously pushing particle A away. To understand how this works, picture 2 boats gliding across a lake, one behind the other. The front boat creates a specific wake that drags or pushes the boat behind it. But the second boat is also continuously creating its own ripples, which travel forward and hit the first boat. Because their speeds and shapes differ, those wakes are completely asymmetrical. The force doesn't balance out. The AI didn't stop there. By running its simulations, it proved that a particle's electrical charge isn't purely determined by its physical size. It also revealed that the radius of a particle's influence, how fast its force decays over distance, varies dramatically depending on the specific environment. The machine didn't just solve a complex equation. It perceived a completely hidden mechanical layer of reality that our strict reliance on classical textbooks had entirely obscured. The value of this experiment goes far beyond plasma physics. The researchers proved that this AI methodology is a universal tool for decoding almost any chaotic multi-body system. In manufacturing, products like paint, printer ink, and cosmetics are just millions of microscopic particles suspended in fluid. By tracking how those individual particles interact, this system can instantly optimize their formulas. This connection works because both systems are many-body environments, places where the behavior of the entire group is dictated by thousands of individual agents pushing and pulling against one another. To a physicist analyzing the data, a human tumor presents the exact same structural challenge as that vacuum chamber. When cancer cells break away from a primary tumor and migrate through the bloodstream, they aren't just floating aimlessly. Their movement is governed by a highly complex, chaotic web of individual cells pushing against each other, pulling on tissues, and reacting to chemical signals. If a graph neural network can successfully map the invisible forces shoving plastic dust around in a vacuum chamber, it can be deployed to decode the exact physical mechanics driving cancer metastasis. We are watching the role of the human scientist evolve in real time. The job is shifting from personally deducing the laws of nature to architecting the neural networks capable of finding those laws for us. But this isn't an autonomous magic box that prints out universal truths on command. It took a dedicated team of physicists over a year of constant tweaking, debating, and verifying to build a network that could actually yield accurate results. Yet it forces us to ask, what happens when an AI eventually discovers a profound truth about gravity or time that human minds are simply incapable of comprehending or manually verifying? The greatest challenge of the coming scientific era will not be whether we can build machines powerful enough to decode the universe. It will be whether we have the capacity to understand the answers they give us.